So, last lecture I discussed asymptotic freedom. So now we have QCD, and we know that the tone coupling is actually more if it is evaluated at a large scale. Then if we have a sufficiently inclusive process which the characteristic IND scale, we can think that the hadron are formed by weakly interacting working duo with partons that we call all of them, while at some lower scales of the order of the hadronic scale, say 1 GeV, the interaction between the partons becomes strong, so this parton will interact strongly and will form the hadron, and if they are produced at high energy, they will hadronize. Owing to this property of asymptotic freedom, if we are interested in some say highly inclusive process, some high energy scale, we can try to write down a picture, which is called Perturbative model picture, which somehow we factorize phenomena of short and long distance. We factorize the interaction of small distances, and then from the hadronic particle, which is related to the human interaction. So let me consider a few examples. The classical one has collision between plus and minus through a photon, a virtual photon of the Z, and consider the total cross-section for the hadron. So the Perturbative model picture is the following. We have the plus and minus pair that are related, and that is a Q-Q-bar pair. Then the Q-Q-bar pair will produce other gluons, and also the group, all possible QCD interaction. So these objects are produced at a scale here, at the momentum scale that is the order of the central mass energy of the collision. Then radiating gluons and interacting between themselves, the quarks will decrease their energy up to a lower energy scale for the order of the Q0, and where this scale is something like 1 GeV, 2 GeV, 0.5 GeV, the scale which is much smaller than the total central mass energy. At this point, the interaction becomes strong, and then this gluon and quark will interact and will produce light. So this is a kind of factorized, let's say, semi-classical picture of it. And this is essentially, this term is essentially what is called Perturbative model contribution, the one that gives the cross-section, which is and the lowest order cross-section, which is 4 pi alpha squared, is the defined spectral constant, so it's this square, times the number of columns, then the sum of the charges of orbital differences. So this is the quantity that I show you in the second day. Okay, this is the first step, the very high energy scale, and then we have the interaction. So we start with the scale which is larger. So I mean, up to some point, this interaction can be considered controlled by alpha strong at the scale Q. And there are many interactions, so many powers of alpha strong that can be exchanged, that are included in this kind of interaction. And since alpha strong is very like 1 over log of Q. Okay, put here like this. 1 over log of Q, where Q is determined. This kind of interaction are suppressed by energy, because the log Q is applied and is the inverse power. But this kind of suppression is suppression of the time inverse powers of the work. Okay. And then there is a stage, the last one, which is the atomization stage, in which essentially you can think that these interactions here are suppressed by some power of the energy. Okay? So this is the kind of solution. So we factorize this high energy interaction essentially in 3 steps, a very trivial one, then the ratio that are more sufficiently high energy, but they are suppressed at high energy only with the inverse of velocity. And then we say here is strong interaction that anyhow are suppressed by power of the total central mass energy. So 1 GeV over, so if I'm at left, 1 over half with some power. Okay? So in effect approximation, we can invert all of these because the correction to this part of the picture. Second approximation, we can consider this and this one. And at that point, then we can add all this kind of. Okay, this is the total procession in plastic acceleration. And then we can apply this picture. So this is a very inclusive process. I'm just considering all possible atoms that are used. But then I can try to extend this picture to a process which is less inclusive. Again, I consider the aggregation, the rotational atom, but now I observe one single atom in the different state, plus anything. Now, so I detect exactly one single atom, plus anything. And I measure the momentum of this atom. And then I can compute the included procession from producing this atom. Okay? The Lorentz invited procession. So, part of the picture tell me that, okay, I have produced this object. They will interact this way. And eventually, from the interaction of one of these objects, which has been primarily produced, I will have some transition from atom to atom, from the form of this atom, through a mechanism which is non perturbative. Okay? So, this picture, and then if the final atom has momentum p, I can say that the original work that produces this atom plus anything, that is a fraction of the momentum which is larger, because it produces the atom plus something else. And in this fragmentation process of the quark, the original particle lose a fraction of its momentum equal to that. So it is that the moment here is p, the fraction that is lost in this process, so the original momentum of the quark goes on with that. Then I can compute this object this way. So I can simply take the concession for producing a quark and a quark pair, and then I multiply that by some probability of this fragmentation process. Back to the following, the vortex. Okay, so the concession for reducing this pattern, including production of this pattern, times an object is called fragmentation function. So the probability that an originally produced pattern will transform in this kind of pattern is changing or losing some fraction of momentum, plus anything else. Then I can try to do the same for other processes. Now I can try to consider the electron-hadron collision. So I'm having the initial state. So the electron and the hadron will interact. If I get the electron in fast state. So this scattering of the vector photon, and they introduce anything in the fast. Typically it's ion from the interaction. So I can think of this process exactly in the same way. So the proton, or the hadron, is made by quarks in gluon. So I consider the interaction of the electron with one quark from the proton. And then this interaction will produce some final state. And the rest, the remnant for the proton, is going to fast state and everything will produce time. Okay? So, now I have a proton hadron with momentum p, and inside the hadron I can find an almost free force. Because it is changing into large. With some fraction of the momentum of the hadron. Okay? Then I write the concession of the collision of the atom in momentum p. I can also have the glue, so any kind of pattern. The concession as the interaction of the electron with the parton, inside the proton, multiplied by some probability function. The probability function is the probability to find inside the proton a parton with some momentum fraction z for the proton. Okay? So this object is called, this is a non-perturbative object. And it's called fragmentation function. Of a parton to electron. And this object is called parton distribution function, or parton density. So you have the distribution of the parton inside the parent of the parton. Then I can apply this picture. So I was considering essentially everything included over the parent spectrum. Now I consider one atom that is detected in the fast state, Here I'm completely included over the final state, but one atom in the state. And then I can try to go to atom chlorine, have a chlorine or one. So I can simply take this picture, multiply the interaction with the atom. Like I have two atoms. They collide to produce the vector boson that decay into electron. So I can think of the production of these high mass states. I have one quark from one atom, one and the quark from the other. They collide, so they reduce the vector boson, plus anything in the center. And then here, this object is exactly the same object that I see. Okay? The probability distribution of quark inside the atom. So it's the same pattern that is in the derivation. So I think it's the question is if the atom is moving to P2, this object, the pattern inside the atom has some fraction x2 of the moment 2. Here I have atom moving to P1. The quark is collide some fraction x1 of the moment 2. Okay. So one atom that produces the vector boson plus energy. I can do the intersection of two partons that collide and produce the vector boson. And I multiply this parton intersection with the probability of having those partons inside the atom. This is a picture that is essentially based on both proposed before the discovery of QCD. But essentially the justification of this picture because of our authority. So, according to this picture, compute inclusive Arquette intersection, essentially in terms of parton intersection. This one. This one. This one. This one. And these are computed in terms of cortical one. So these are the so-called Arquette intersection. Parton intersection that I compute to the lowest order perturbation zero, including hydrogen. And then, eventually, depending on the case, I multiply this object that I can compute times some objects that are non-perturbative. But these objects, fermentation functions, atom density, depends on the atom. They do not depend on the process. Okay? They are the same. If I produce W, they are the same if I produce Z. They are the same if I produce boson. Or if I do the same in this case. Okay? They do not depend on the process. Just the property of the atom. How partons are distributed inside the atom. So these objects are non-perturbative, but they are fully reversible. They don't depend on the scattering process. So,
can I ask, in that formula for the fragmentation function,
right?
why is your integration measure dz over z squared?
In the first case, it depends on the definition of the inclusive procession. If, well, depends on the definition and on the definition of D. You can change the definition of D, including some part of that. That is, let's say, the conventional definition in such a way that the integral of z of this object is essentially the multiplicity of parts. If you define z differently, you will have a different factor here, but the integral of z of this object will be something different. That's what I say, just conventional normalization factor. Normalization, z-dependent factor. Anyhow, this is the function of z, so you can, in principle, change the definition and include some extra function of z. Okay, so these objects are not perturbative, and let's say, within perturbation theory I cannot say much about it. But anyhow, they are universal. So for instance, I can try to relate that to the non-perturbative structure of the theory. So in principle, if I'm able to solve the theory, I can define this object, and I can compute this object in a non-perturbative way. For instance, using that. Anyhow, even if I don't know how to do that, the main point is that these are universal. So I can compute the Platonic concession for a process. I can compare data for that process with my prediction, and from this prediction I extract information from the pattern integration. So I can extract information on pattern integration from some processes as a phenomenological input, and then I can use those information that I have extracted from some process to predict on the other processes. Okay, this is essentially the meaning. So this object have somehow a role which is an output of Fatron. We don't know the exact value of Fatron. In the theory view of Fatron, but the exact value has to be measured. So suppose you don't know how to solve QCD non-perturbatively, you know that there are these non-perturbative objects, and you try to measure them in one process, and then you use them in another process.
About the distribution functions, is there any advance in non-perturbative QCD, lattice QCD, or something to calculate them? Or?
Yes. There are results. No, it's not a simple logic because let's say there are numerical calculation of some integral of this from they're called n moments. Anyhow, there are perturbative information that are directly extracted from the theory. Anyhow, I'll say quite a bit more about this object than the so, this is a kind of factorization picture which is intuitive, reasonable. The point is whether this picture is correct or not. And the answer is that I think there is no rigorous proof of this kind of picture. Rigorous, I mean, in terms of physics. Not rigorous proof in the most general case. Okay? So for all of these, there are certainly rigorous proofs for the total concession, the pattern combination, and there are rigorous proofs field theory for the total concession in the left hand. Anyhow, I mean, for all the other processes, we don't have a proof from field theory point of view because it's a difficult concession. Anyhow, even if we don't have a proof from that principle, at least at present, we can try to see if, let's say, this picture is somehow self-consistent. If it works, if it can be improved, if it can be made, can be used to make something prediction. And the answer to this question is that, okay, let's try if it works. And the only way to see if this is a self-consistent picture is to start to compute the declaration, to start to model, and to see if they behave exactly, or let's see, if they are not in contradiction with candidates. So this is just the beginning, Perturbative QCD, because at this point, essentially part of what I do. So the beginning is starting from this, we start to compute for the traveling and see if they fit in. That's what I can do, I can start to do today. Just a comment about the language. Typically, when you do perturbative calculation in QED, you label the calculation with first order, second order, third order, eighth order, and this number typically refers to the power of the fine structure number. First order, second order, or to the power of the electron charge. So that's why typically you can have eighth order calculation because this is fourth order enough. Anyhow, this is typically the level that we use, or that what we use in QED. Now in QCD, since we want to deal with many different processes, we typically don't think about the orders in numbers, because all these different processes can start at different order in alpha. So typically, different processes have the lowest order, which is the mean power of alpha. It can be 0, as in the case, 1, 2, depending on the process that we are using. So typically, the level that you use in QCD is linear order, which is the lowest order in alpha for that process. Then, when we add the correction of the alpha, we call it an exponential order. Then the second correction is an exponential order. Okay? Grazie a una Okay, so let me start to see if this picture works. And the simplest case where I can try to apply this picture. So I have no hope to compute this object, which is very logical. So this is really abnormal. But I see if I can compute the first correction of this picture. Corrections which are large, which are suppressed, but they are not suppressed as power, but they are suppressed as this power of 1. So these are, if I go at high energy, this correction are more important than V1. V1 is much more important. So I want to compute this. Okay. So essentially, I compute and then I'm making a continuous correction, a QCD correction, and so the electron and positron sono simili a each other. So here matter is the relative connection to this box, okay? So I forget about it, because it's trivial, it can change when I do it. So, So the linear order has this one, the square of this one, will give me then I go for the first order in alpha. And I can produce a groove. Whenever I step the amplitude, to produce the constraint, I have to square. Okay? Then I take the diagram and the complex conjugate, so I get two diagrams and square I get 4 diagrams. Okay. So when you tell the amplitude, you really have this kind of diagram because you sum of the spin. And then this is the 3 particles in the final state the real particle. So they are on shell. And so I draw a cut that these are on shell. Okay, so this is the real initial, but then, you know, we have also neutral selection that goes into that order. The neutral selection will be the big bundle. Progression to the process times the lowest order, the complex order. Okay. Plus the complex conjugate this diagram, essentially, I don't know, you get this with this, and this with this, so you get the real part of the diagram. Okay? I'm just drawing this diagram times this transition. So you see essentially that they're the same diagram. Okay. The only difference is that here you have the real gluon, here is the victor, and so the particle which are on shell are these two by the gluon victor. Okay? But you know, you don't have any difference, you put follow them off share, and these two contributions will be exactly equal. Okay, so real linear contributions are very similar, but the diagram, but certainly the kinematics is different. Okay. And I'll be back later and to the point. Now, to go ahead, I need to do a bit of kinematics. I consider only the real distribution, where the kinematics is more involved. To complete the closed section, I have to take the matrix element and to integrate over the free space. So I need the kinematic variable of the solid. So I have three atoms, momenta T1, T2, T3. Obviously, the total momentum is equal to the momentum of the plasma to the moment of the photon. Okay, now, I introduce this variable, which are essentially the energy fraction of the particle in the central mass frame of the collision. So I can have definition in fully Lorentz invariant. Now, in the central mass of the collision, it is the energy of this particle divided the energy of one of the two logarithms. Okay? So these are energy fraction, and of course they are positive. Then I have momentum conservation. You can easily realize that momentum conservation implies that this is equal to. Okay? So the sum of the energy is equal to the energy of the electron and of the proton. Then I can also think about the angle. So let's see. Take the scalar flow between T1 and T3. I get momentum conservation. And since the orbital mass is equivalent to this stuff, and T1 plus T3 is Q minus P2 square. So I get Q square minus 2 P2 by 3. Okay, so, and if I apply this in the central mass frame, I have 2 times the P1 is 3, 1 minus cos theta, the relative angle between 1 and 3. And this is P square times 1 minus 2. So I see that this scalar product is positive definite. So this has to be positive definite. So again, I get that 1 minus x has to be positive. So all these variables go in the range 0, 1. And I also think that, for instance, if I take the limit in which the angle 1 and 3 become parallel, is 0, so this corresponds to the limit in which, for instance, x2 is unity. Okay. So this is just a bit of cinema. Okay, so now the phase space that I have only 2 independent variables. So in the plane x1, x2, this affected, okay? Limited by the boundaries, whatever is boundary. So that's it. So I have to integrate over different vectors. Then let me show you that the region has some interesting subregion. So let me enlarge so this is the region where x1 is brought to unity. And according to these arguments, this is the region where the angle between 2 and 3 vanishes. So when the gluon related collinearly with one. Analogously, I have this strip here. This is the region where theta 1 3 so where the gluon is parallel to the other coordinate. And then I have another interesting region, which is the coordinate, in which both x1 and x2 are brought to unity. So by moment of conservation, 1 plus 1 is 3 has to vanish. So this is some kind of soft region when the gluon that is produced inside the cake is very, very small. Okay. Now I can start simulate integral. This is the translation for the real part. Okay, the phase space. All the content that I have done. And then I have this object which is quite matrix element. That depends on the moment. So now the object will depend on the integration of expansion and fluency. And this object gives a tensor which is exactly proportional to the one vector and can be scalable. The overall procession was just a constant. I mean, one way to sort it. I cast in scale, this matrix element for the unit of the terms. And then this matrix element is obviously proportional to a factor, to power g. And then it's proportional to the charge of the quark, because the quark that radiates move. So the total factor is CF. And then we get the factor of 2 pi, if you compute it. And then a very simple structure for the matrix element. Very simple function to be integrated. However, you see that this function, which is the matrix element, is singular when x1 is equal to unity, and it's singular when x2 is equal to unity. So it's also singular when s3 is equal to 0. So this matrix element is singular to not to the boundary. Not only singular, but this singularity is not integral. because okay. So I was trying to see if this factor model picture was improvable consistently, and I immediately find a problem, which would be a disaster. So definitely something going on. Eventually, it's not a disaster, but it's a signal of a possible data. So, where this singularity comes from? This singularity comes from not the ultraviolet syndrome. There are no ultraviolet, only radiation. They are coming from the infrared region. They are coming from the region where one particle is very soft, with a very small energy, or two particles are collinear, so a very short distance, a very long distance, I mean, very large space-time. All these problems of infrared origin, and they are related somehow to the long distance part of the process. So they are coming at very soft energy, so it's something is related to long distance. Of course, I'm doing calculation with massless particles, and they avoid atoms. So if I have atom, the energy cannot go to zero. At least it's bounded by the mass of the atom. Okay? So in any, let's say, if I try just to replace this part with atom, certainly I will have some kind of cutoff. And this cutoff is something dimensionless related to this scale, the cube. So it's a fraction, like Q0 can be the mass of the particle. Is the cutoff, the spin is singularity. So QCD is not exact, possibly. I use massless particle while they work like massive particle. Nevertheless, if I simply use this kind of cutoff, which is a physical one, to compute this property, what I get is that these terms have a factor of alpha in front, so this correction. Then I have this integral, which is the logarithm of the cutoff. Now I know that this cutoff and this logarithm of the cutoff is essentially something that is proportional to log Q. And then alpha is 1 over log. So I was starting saying that, okay, I use perturbation theory because these corrections are suppressed by power of 1 over log. Now I find the infrared divergence. I say that I can regulate the divergence physically, but I get an extra power of log. So this object is what they use. You don't get more recursive. So what I'm doing here is a perturbative expansion in which I have a linear object, then a projection which is alpha times from the integration of the matrix element 1 over alpha, which is this cutoff. Then at the next order I will get alpha square times 1 over alpha square, which is the square of this cutoff. So, you know, everything looks consistent in the sense that I don't get any divergence if I introduce the cutoff. But what I get is that I have a vectorial expansion that doesn't make sense. Each order is as big as the previous one. So I cannot use perturbation theory. I cannot make this picture predicted particularly. Okay, so in summary, the presence of this singularity signal the fact that there are possibly effects perturbative, but in reality they are not powerful places. So I have some kind of possible equation. I'll come back later to this point. Let me have a closer look at the structure of the singularity. So the matrix element plus pure algebra was just an identity. Just triggers. So here the singularity, and this object is not the singularity. So I can look at this. Another trivial identity. Simply partial fraction plus so I write a matrix element in this way because in a sense I can factorize this singularity. So this is the source singularity when you split to 0. Then here the collinear singularity when theta 2 to 0. And here I have another collinear singularity with theta 1 3 equal to 0. So I split the matrix element into two components. This one and this one. And each term has a collinear resource singularity. So roughly speaking, I can write the matrix element neglecting these harmless integral terms. So relative fields of negative sign are depends on. And the sum of two independent definitions. Okay? Faster like this, faster like this. So I can think of the matrix element as the lowest order part times the probability I produce a quark and a quark, then I have another step, and I have the splitting of a quark with a quark and a gluon. Where these two are collinear. So, 3, which is this term, plus radiation collinear to the other table. So what is the probability of splitting? I erase the numerator. The numerator was X independent. Here. So if you remove the numerator, so I have, let's say, sigma 0 times some probability, for instance, for this splitting, and another probability for this one. And this splitting probability, when we came to 2, 3, I reinsert the face-to-face contribution changing parts. Here is one is two. And this object depends on X3. The one I was taking from here, and then that was in the numerator coming from the and so let's say, in the soft equilibrium probability interpretation of the deviation. I write the matrix 7 square exactly with this kind of factor. And then, because of the kinematics, this is equivalent to the d cos theta, to 3 over minus cos theta to 3. Okay? Just the relation that goes down at the beginning. Then, if you go to the collinear limit, which is 2 and 3 are parallel, essentially you get d theta squared to 3 over theta squared to 3. Okay. Then if you take the soft limit, you get ds3 over ds3. Which is essentially the same as de3 over 2. Very accurate. So this kind of double logarithmic spectrum is the standard d omega over omega, and the spectrum for soft photon emission. Okay? The energy of the energy, and this is a collinear spectrum. So the probability of radiating a soft and collinear gluon is the next, the soft and the collinear. Okay, the matrix element, I've written the matrix element in that way. I can avoid that, but that is for fusion purposes. Now, I can try to integrate the matrix element for the real part. So, integration the terms which are record. So I integrate on the simple terms. So I get one return, I change variable, and here is the data function, 3 variables, and take over 1, and they use angle, energy, as good and I get the Jacobian for the leadership. So then we come from the integration of the data function. So just face-based change of time. Then I will get the derivative which is argument that you can integrate. This part of 2 that you can integrate. There are 2 times by this. One side is here, and the other one to consider. Okay. done anything. I just rewritten the previous program in a different way. Okay, don't forget about the video. I also have the video contribution together. The same order enough. So as I said, the picture diagram looks exactly the same as the real one. Certainly, apart from the phase space, the phase space is different. In one case, there is an integration over 3 moments. In the other case, there is an integration over 2 moments with the virtual group. Okay. The virtual, let's compare the virtual group with the real one. I can integrate in the ultraviolet region. I can take the singularity, ultraviolet singularity, and normalize it. They are included in the normalization. But then there is also the loop integration of the infrared region. Because the momentum can go from 0 up to the scale of the order of the energy. And so I can write the loop integration as the integration of the energy of the virtual component, which goes from 0 to infinity. And then the integrand looks exactly the same as the real one. And then I neglect the ultraviolet part because we know that chemically the normalization. So I end up with the soft part of the loop integration. And then just look at the diagram, I see that they are really very similar to the real one. And if you do the calculation, you find that they are really in the equilibrium. Essentially because this equality comes from unitarity. You produce a QP by pair, and then they eventually will give the price value. So whatever they do, once they are produced, they will give rise to atom. So the probability of having atom at the end has to be conserved. So essentially, the real and the virtual contribution should be cancelled to conserve probability. I will say the virtual one should be equal to the real one, but for the minus sign. So there is a minus sign in the difference between real and virtual. So let me add a virtual. I said that in the infrared region, essentially the virtual contribution is exactly equal to the real one. The matrix element is equal. So I will get essentially this kind of contribution of the matrix element. But now the kinematic is different. Momentum conservation, not momentum conservation. Momentum conservation. This integration is not constrained by the energy of the other two parts. The momentum conservation is momentum conservation of the two. So the phase space from momentum integration is different. And you simply get minus 1 because the integration is just a kinematic of this energy. And this energy conservation is a factor. The minus comes from the matrix cell. The difference between unity is just a different phase space. So at this point you combine the two, and you see that this kinematic effect in the limit when theta to 3 vanishes, or x3 vanishes. In both cases, this also vanishes. Okay? So this difference we have like okay. So what you see, you have the singularity, 1 over theta square, 1 over x3 in the real, the similar singularity with this one. But then real and virtual are somehow equal, and there is a phase-space cancellation of this. So when you add the real and virtual to compute the total procession, this singularity disappears. So for the total procession, you get a picture which is completely consistent get the cancellation of infinite singularity. So that means you combine here and here, you do a calculation, you get all level. And then from the integration, you get if you do the calculation with 3 over 4. Okay. So this is just a discussion and you cancel the singularity. Happening here. Okay, so this Perturbative picture is consistent for the toric section. That is all. Okay? I get a correction which is really about no short distance and no long distance enough to infinite. So everything which is long distance cancel when you do the perturbative. And then you can prove that if you can also try out. I cannot do the calculation too. So therefore we have to give you a friend. And then I have 2 comments. As a center of the real matrix element of the real contribution, I tell you that the phase space is typically flat when you produce Python. While the matrix element is enhanced, not flat. The matrix element is enhanced when you consider region where you have the production of Python which are collinear on one of the Python itself. So if you look at the structure of the final state instead of computing signal of the structure, you expect to see a signal of the structure of the matrix element. So the matrix element QCD gives an enhancement to some phase space region. So you expect the structure of the hadronic final state that you see as a consequence of QCD matrix element is the same. There are bunches of coordinated hadron because you have enhanced probability for collinear relation and a lot of short stuff around. So this comes exactly from the structure of the matrix element. And so you expect to see that, and you see that in the net pattern. You don't see isotropic event. So you see this kind of jets, like short pattern. So second comment, okay. I have this cancellation of infinite singularity. This tell me that the total cross section can be computed in perturbation theory safely. This part of model picture that can be improved step by step for the biological neglecting power connection. Neglecting application. Now, can this picture be extended not to another procession but to less inclusive quantity? Can I compute in this way only the total procession? The answer to the question is that you can extend this picture. The mechanism here was a kind of cancellation of infinite singularity. That was the line this picture to be considered. So eventually I can extend this picture to other server because this kind of say, equality or universality of the real is to order and for any process. Provided you don't do something wrong with the matrix, with the quantity that you want to measure. So let's give the total procession. Now let's suppose just a sketch that you want to compute something with not the total procession, but the procession which is some experimental cut, with the procession for producing reject or project. Okay? So for this kind of process, you will contribution. middle of the contribution will be the integral. Suppose that I consider a production of 5 jets. So you have to start with the 5 parts of the final state. Otherwise, you can't get it. So you have a linear order term with a matrix element for producing a certain number of parts. The minimum amount of parts that are necessary to measure the result. Okay? So let's say that you have m parts, the minimum one that you can get. And then you will have the integration of the phase space, Lorentz-Divine phase space for producing these n factors. And then you have a 3-level matrix element for producing both n factors square, it's just a procession. This will be the contribution to the total procession. And consider the matrix element and integrated with the phase. Now, we are measuring something which is not a total procession. So we are enforcing some measurement function. I can think of having some theta function, some cut in the phase space, or the definition of the measurement. That depends on the fact that you have n factor, and that depends on some jet observer that you have measured. You can measure different things, and this will be a function of the momentum of the final state part. Okay? So the function of the unity is the total contribution, to the total procession. Otherwise, you are measuring something different. It depends on the momentum. Abstract definition of the measurement. Okay? Now, we go to next to the order. And you have to consider the real and virtual contribution to this scattering with the impact. Okay? So the real contribution will have one more part of the final state. And the virtual one will have the same number of parts of the final state, but one more part in a loop. Okay? This real and virtual contribution have an expression that is exactly analogous to this one. Okay? Correspond to phase space, matrix element square times measurement function. And the virtual will be the one loop matrix element square, integrated over. So I'm just proceeding in close analogy to what I did for the total procession. The only difference is that now I'm not integrating over the whole phase space with the ways of the unit, but I'm mostly some constraint over the phase space. Constraint due to my measurement. Okay, both of them are divergent because they are obtained by the matrix element square, where it is allowed the radiation of soft collinear factor. Radiation of soft collinear factors fulfills some factorization property, where for the real matrix element, now I have the matrix element is the m plus 1 part. Okay? One more than the previous one. It depends on all the final state moments. Okay? So, m plus 1 of them. Okay? Well, and then if I compute this matrix element, there is where one of the parts is soft. O collinear to another one. So let's say when one of the parts, PI, is given so, or PI collinear for another part of the J. The matrizione factoriale is exactly the same way as I wrote the previous matrizione. So we get the factor, which is the three-level matrizione with one less factor, and a function that depends on the two parts of the term in the software solution. So this function is exactly the same, the function that depends on the energy fraction of the software that I wrote before. This is a sketch. I mean, all these formula can be written down, everything up to the very last function. I have the same factorized structure as for the previous matrix. And this object is universal. Why? The matrix element that remains as a factor of it isn't process dependent. But the software coherent factor that enhances the production is process independent. That's why the factorized structure that I wrote is probably and then for the virtual part, now you have the virtual part, but again, the matrix element that now has an factor. And if you consider the momentum region in the loop, where the momentum is soft, in that soft or coordinate to some of the thermal particle, is again proportional to the three-level matrix element. The same number of particles without the loop, times a singular factor that is coming from the integration of the loop in the infrared region. And again, this universal integral part of the loop is universal and is equal to the one that defines the real mass element. Apart from an overstand. Okay, so I tell you that what I did for the explicit example of plastic minus annihilation is true in general. There are two ingredients in the infrared software collinear region. You always get an enhancement direction factor for the real and for the virtual with opposite sign and which are equal. Only the divergent part, and then for the rest is different. So now we go and we combine real and virtual. Yeah, all the terms which are fine, which are not coming from the region, they are separate and fine, so then we give some number in front of us. And then there are these contributions which are separately divergent in the infrared region from the real and the virtual. I combine only these two terms. So both of them are proportional to the three level. So essentially, I have something which is proportional to the neural contraception. Okay. And then I have the integration over one the extra part that I produce, either the real or the extra part in the loop. And this is the integration over this, and then some overlap. The integration over this extra particle is limited to to the infrared collinear vision. So I'm just looking at where this pattern is the sort of collinear vision. Then I have phase space effect. But the phase space works like that. The total phase space eventually is the same in the soft collinear vision. So the fact here you get a cancellation is that the real phase space and the virtual phase space are exactly equal. So the difference in phase space, total phase space, is not relevant for real and virtual. It was in the case of total perception. And then I get the factor, a singular factor to be integrated from the real. So something related with splitting on the part into collinear and soft. The probability I looked before. And this kind of factor is the same for the real and the virtual part. It is related to the universal behavior of the matrix element. Something related to QCD. And then I combine real and virtual. And for the total concession, I combine the two with the same weight. And now I have a measurement, and the measurement depends on the number of particles that I see. So this measurement function can depend on the number of particles, not only on their momentum. So the real part, I have this function with n plus 1 momentum. And which also depend on these two momenta that can become collinear. And then the virtual. The virtual has only n momenta parts. So the measurement function cannot depend on the momentum of the part inside the loop. You don't measure it. So it is a measurement function that depends on n part of momentum. So I get a minus because the real and virtual are the same weight. And now I have one less momentum than before. The momentum, which I can say is the sum of the two that I see here. So I have splitting for the real, and the virtual I see on the INJ. On my left, because I can measure all this one. So it means measure kinematics. So if this is one, I get 0. But then if I measure something, this is not trivial. To cancel the singularity, this is trivial. I need that this difference should vanish in the soft and collinear vision. It's just kinematics. Have infrared cancellation, infrared behavior in matrix, same infrared behavior for real vision with an opposite sign, relative opposite sign. If I combine globally they are together, I get 0, cancellation of singularity. If I measure something, I don't want to produce any mismatch in the infrared collinear between real and virtual. So the weight of my measurement has to be the same independently of the fact that there are soft and prominent patterns around. So, what I need formally, just some requirement on the measurement of the time doing on the function. I write my function on my measurement as a function of movement, and then when one of the two vanishes, or one is parallel to another, I need this measurement of this function, which is the same function with one less pattern, like the vector. And if it depends on m plus one momentum, it depends on m momentum. All the other momenta are left unchanged, but these two momenta are replaced by a single one, which is the sum of the two. So if these two are collinear, you just the sum of them. I see all of them together. Okay, this is formally what we have to do. In practice, what I'm telling you that you can apply this consistently to QCD perturbation theory to any measurement that essentially it is insensitive to the reaction of some particle, because the fact that measurement cannot change if you negate some particle, and it is insensitive. It is insensitive to the reaction of collinear particles. So you cannot distinguish if two particles which are almost collinear are relative particles or only one. Okay? So in all your measurements, you need this kind of requirement, which is called infrared and collinear. This is a requirement for unsteppable to be computable in perturbation theory. So this does not mean that other observable cannot be measured. They are fine. Anything that you can measure is measurable by definition. The point that if you are measuring something that has not this kind of property, that means that you cannot make a distinction between perturbative and non-perturbative causation. Or, there is no effect which is not power supply. Everything, the strong interaction is only the order you, even if this process is very high energy. In a process of very high energy, to perform a measurement of an observable which is not infrared safe, that observable depends on the mass of the particle. If you have a jet with 500 GeV of certain momentum, and the jet is defined in a way which is not infrared collinear safe, the problem of the jet will depend on the mass of the particle. The mass of the particle or the count depends on how many count and pi are in the jet. Okay, can show an example tomorrow. If you wish, I can give you a couple of exercises. I can do the total concession for plus or minus an electron. Actually, I found zero, because what I computed is zero. All the interesting part, which is finite. So, 3 exercises related to the calculation, to the extraction of the total concession program. And we're going to need the real, the virtual, and then the integral. The only point that all these integral and the vector separately. So you have to compute the real and virtual separately in some regulator. And use the same regulator consistency for the other. So yesterday I was talking about the dimensional limitation that can be used to regulate the ultraviolet intensity. If you change the number of dimensions, instead of everything. So the dimensional regulation is the epsilon is positive equal to 0 to regulate the ultraviolet. If epsilon is negative equal to 0, you regulate the infrared. So we can use the dimensional organization to perform calculations which are infrared singular. And all the singularity will appear again as a pole. So that's why dimensional organization is particularly useful in QCD, because you have both ultraviolet and infrared intensity, and with the same organization you can regulate both of them. So the fact that the sign compute simply the virtual pattern. So there is one loop, matrix element, for a plus and minus, you divide the virtual loop. That means that actually non scegliere anche tutto poi il virtual control più basso. So this, the one loop contribution to the production of the virtual critical. No operaria critical verso the virtual function. I am asking because the volume calculation, not the calculation of one die. There are 3 diagrams to be computed. If you're not clever, you will mind now. And one loop diagram that can be computed in the calculation. So this is the real part. And you will find in the mechanical detection that is the formula that is square. And there is something you don't perform Then, second exercise, you compute the matrix element, 3 level, for producing QQ by the same matrix element that I wrote down. So the one called X1 square plus square over 1 minus 1 minus 2. But you do the calculation in dimensional relation. So if you compute the matrix element in D dimension without any integral, you will get correction of all directions in the matrix element. But this correction of all directions in the matrix element are relevant because after the integration you will get one and eventually. So you will get the same expression plus some times the whole direction of the numerator. So this is the second exercise, just into the real matrix. Third exercise to compute the transition. Essentially, you integrate the real matrix element in D dimension. From that integration, you get poles that cancel exactly the virtual. You can divide it with the electron distance. So these are 3 different exercises. To do the last one, you can proceed in 2 ways. To complete the concession, you can either do first the real and then the virtual, and then use your result to complete the concession. Or otherwise, you don't want to complete matrix element, you take the real and the virtual from the virtual. literature, you simply integrate linear, you see that when you integrate linear, you can also see that